그럼 오늘 발표는 영어로 하는 거죠? 제가 영어가 짧지만 영어로 발표 준비해서 영어로 발표하도록 하겠습니다. First, thanks to Professor Sangjune for inviting me, and thanks to members at KAIST for coming here to listen to my talk. It's my honor to be here and give a talk at KAIST. So this is joint work with Yoshiharu Koyakawa at University of Sao Paulo and Wojtek Rodel at Emory University, who is my advisor. So the title is The Maximum Size of a Sidon Set Contained in a Sparse Random Set of Integers in the N set. So if you read this title, you can you can understand the topic. So first, you can read the word, the maximum size. So this result is something about an extremal problem. And you can see a Sidon set and integers, so which are the object of this talk. And you can read the word of a random set. So this result is something about randomness. So based on this order, let me explain the background first. So let me first explain extremal problem in additive number theory. So let the N set is integers between 0 and n-1. Then a typical extremal problem in additive number theory is the following. So we want to know the maximum size of a subset of the N set which satisfies a constraint. So in this talk, we will take a Sidon set as a constraint, and now I will introduce the definition of a Sidon set formally. So let A be a subset of the N set. An integer set A is called a Sidon set if all sums A1 plus A2, where A1 and A2 are in A, and A1 is less than or equal to A2 are distinct. So let me give you an example for this. So first, a set 1 to 3 is not a Sidon set because 1 plus 3 is the same as 2 plus 2. But on the other hand, other set 1 to 6 is a Sidon set because when you think all possible sums of two elements of A, they are distinct, like 2, 3, 7, 4, 8, 12. So let me give you an equivalent definition, which will be used in this talk. So solution A1, A2, B1, B2 of the equation x1 plus x2 is y1 plus y2 is called a non-trivial solution if the solution satisfies the set A1, A2 is not the same as the other set B1, B2. So for example, this kind of solution of the equation x1 plus x2 is y1 plus y2 is so trivial, right? So we don't think about this kind of case, but if you think this solution, then the set 1 and 4 are different from the other set 2 and 3, so this is non-trivial solution. So this kind of thing will be also trivial solution. Okay, so and then now we can define Sidon set based on non-trivial solutions. So set A is called a Sidon set if A does not contain any non-trivial solution of the equation x1 plus x2 is y1 plus y2. So based on this equivalent definition, let me explain previous examples. So first, the set 1 to 3 is not a Sidon set because 1 to 3 contains a non-trivial solution. 1 plus 3 is 2 plus 2. But on the other hand, 1 to 6 is a Sidon set because 1 to 6 does not contain any non-trivial solution. So now let me explain the extremal problem with Sidon sets. So we'd like to estimate the maximum size of a Sidon subset of the n set. So we define capital F of n as the maximum size of a Sidon subset of the n set. In 1940s, Additive, Turan, and Chawla determined what capital F of n is. So they got the result like capital F of n is square root to n times 1 plus little o 1. So for example, if we have if we consider integers from 1 to 1 million, then the maximum size of a Sidon set of the integers, it will be 1,000, something like 1,000. Yeah. So this is an important result in 1940s. And now, in this talk, I explained related extremal problem on a random subset of the n set instead of the n set. Actually, this kind of research line is one of the most important developments in combinatorics over the past 20 years. So for that, let me explain the random subset. So let NP be a random subset of the n set by choosing each element independently with probability p. And let capital F of NP be the maximum size of a Sidon subset of NP. So now situation is the following. So instead of considering the integers from 1 to n, we think a random subset of the set, and we want to understand what will be the maximum size of the Sidon subset of the random set. And random set will be like NP. So if P is 1, this is the previous Additive problem in 1940s. Actually, this kind of extremal problems were studied for random graphs by Haksa, Koyakawa, Uchak, Rodel, Ruchinsky, Schout, Steger, and others. And about capital F of NP, there is a recent result by Collin, Gowers, and Schout, so which implies the following. The following almost surely holds. In here, almost surely means the probability that the following event holds goes to 1 as n goes to infinity. So if P is far smaller than n to the negative 2/3, then the size of capital F of NP is NP, which is the size of the random set itself, because we think n integers and we choose each element with the probability p. So the expectation of the size of the random set will be NP. So this tells us that if p is smaller than this threshold, then the size of the maximum size of a Sidon subset of a random set is same as the random set. On the other hand, if p is greater than n to the negative 2/3, then capital F of NP is far smaller than NP. So this theorem tells us the threshold for the property that the size of the maximum size of a Sidon subset of a random set is the same as the size of random set itself. So in this talk, the goal is to study the behavior of capital F of NP for every p. not just for about some threshold. So first here, based on the previous result, let's try to understand the behavior of capital F of NP. So set x and f of x as np is n to the x, and capital F of np is n to the f of x, which means that x is something about the size of the random set, and f of x is something about the size of the maximum size of a Sidon subset of the random set. So in this figure, the graph of y's x with a black dashed line means the size of a random set. So you can see this line. And the graph of y's f of x with a red line means the maximum size of a Sidon subset. First,
what is y?
Y, so this coordinate, you mean? So y is, so x and y is something about exponent. So if y is 1, which means that the number of the size is n to the 1, which is 1. So I just wrote down the exponent here. So, okay. So first, when x is between 0 and 1/3, by a simple deletion method, we know that the maximum size of a subset, the maximum size of a Sidon subset of a random set is the same as the size of the random set. So the red line is the same as the black dashed line. And the result by Cullen, Gower, and Short tells us that this point, when x is 1/3, is the last point, such that the red line is the same as the black dashed line. So which means that after this point, the red line should be lower than the black dashed line. And when x is 1, the result by Additive, Turan, and Chawla tells that when x is 1, the y coordinate is 1/2. So in here we have this point 1, 1/2, which means that f of n1, so which and p is 1, is n to the 1/2. So this will be n, which is n to the 1. So the x coordinate is 1, and the y coordinate is 1/2. So this is what this figure tells. So we want to know the behavior of the graph of the y is f of x. But unfortunately, we don't know, based on the previous result, we don't know what is the exact behavior of the graph of y's f of x when x is between 1/3 and 1. So what we know is the graph is between these two red lines, somewhere here. So let me explain our main result. So the following holds with high probability. So again, with high probability means that the probability goes to 1 as n goes to infinity. So for every p with several different ranges, we found upper and lower bound of capital F of np like this. So first, if p is between n to the -1 and n to the -1/3, we got matched upper and lower bound of capital F of x, F of np, up to a constant factor. And if p is greater than n to the -1/3, we got matched upper and lower bound of capital F of np up to a logarithm function. So let me give you a simpler version like this. So instead of 5 lines, I just wrote down 3 lines. So if p is far smaller than n to the negative 2/3, capital F of n is np, which is the size of the random set. So that's what I mentioned before. And if p is between n to the negative 2/3 and n to the negative 1/3, the size of capital F of np is n log n to the 1/3 up to a constant factor. And if p is greater than n to the negative 1/3, capital F of np is between square root to np and square root to np log n. So this is our result. So based on our result, now we can understand the behavior of capital F of np as follows. So the size of the random set is increasing like this black dashed line. And the maximum size of a Sidon set stays like this when x is between 1/3 and 2/3. And after this point, when x is 2/3, this graph increases to get 1,1/2. So one interesting part is this. Even though the size of the random set is increasing, but the maximum size of a Sidon subset is same, up to a constant factor. This is some interesting part. So let me explain the organization of this talk. So first, let me skip the proof of A, because this is by a deletion method. But maybe I can explain a little bit about this. And after that, I will explain the proof of the upper bounds in B and C, which is from here to there and from above. And third, I will give you the proof of the lower bound in B, which is this part from below. And last, I will give you the proof of the lower bound in C, so which is this part from below. So first, let's briefly think about the proof of A. So when we think this part, so now we have integers from 1 to n, and let's think the situation such that p is small. Then first, so we will think random subset over here. And the size of the random set will be np. And after that, we will think about the number of non-trivial solutions of x1 plus x2 with y1 plus y2. So let's say a1 plus a2 is a3 plus a4 is the number of solutions in the number of non-trivial solutions in the random set. Then let's think about the expectation of this. So first, let's count the number of this non-trivial solution in the n set. Then first we have n choices for a1, and we have n choices for a2, a3. And the last element will be determined to satisfy this equation. So the number of this kind of non-trivial solution in the n set will be n cubed. And then now we need to think about random set. And we will choose each element. Let's assume that these things are distinct. Then we will each element will be chosen in the random set with probability p. So the probability that every 4 elements are chosen in the random set will be p to the 4. So if this value is far greater than this value, or on the other end, if this is far smaller than that, then from the random set, by deleting several elements, we can find a Sidon subset which does not contain any non-trivial solution. So this is the case when np is far greater than n cubed times p to the 4. So this is exactly this. So this is when P is far smaller than 1 over n to the negative 2/3. So this graph is about NP. So this is when NP is smaller than 1 over n to the 1/3. So if NP is smaller than 1/3, the maximum size of a Sidon set is same as the size, similar to the size of the random set. So these two things should be same. So I just computed the expectation, but also we need to think about the concentration. Right. Okay, so let's move to the proof of the upper bound in B and C. So this is from here to there and from above. So our proofs of the upper bounds in B and C relies on the cardinality of the family of all Sidon sets of a fixed size in the N set. So let me define B of T as the family of all Sidon sets of size T in the N set. Then we showed the following key lemma, which is about some upper bound of the cardinality of B of T. So let T is greater than n to the 1/3, and omega and sigma are some constant or some logarithm function such that this blue condition holds. Then the cardinality of B of T is far smaller than some fraction times n over T to the T. So here, actually, if we think the family of all sets of size T in the N set, the number will be n choose T, which is n over T to the T. So if we think Sidon set, we have this kind of fraction. Actually, this fraction is small because in this setup, omega or sigma is a constant or a logarithm function, and T is greater than n to the 1/3. So this fraction is smaller than n to the negative 1/6, so which is really small, smaller than 1. Okay, so we will show this key lemma. So first, let's assume the key lemma, and let's try to prove our upper bounds. So if the cardinality of B of T is smaller than that, then the probability that NP contains a Sidon subset of size T is less than or equal to the cardinality of B of T times P to the T. This is based on first moment method or uniform bound or Bourse inequality. So this is usual trick in probabilistic method in combinatorics. So briefly speaking, so if you think this probability, then this probability will be smaller than sum of probability NP contains a Sidon subset, a fixed Sidon subset S, and S is in B of T. So this will be trivial because this will be not so hard. So, and then this probability will be P to the T because so something of size T. Because the Sidon subset contains T elements, so T element should be in the random set. So the probability that the Sidon set is contained in the Sidon set will be P to the T. So this will be like this. And this will be size of B of T times P to the T. So we can have an upper bound of the probability like this blue thing to the t. So if, in addition, if the blue part is less than 1, then the whole thing goes to 0 as n goes to infinity. So the probability that NP contains a Sidon subset of size t is literal 1, which means that NP does not contain a Sidon subset of size t with a high probability. So if we have two conditions, then, so first condition is from the condition of the key lemma, and second condition is about the base. Then if we have two conditions, then we can say that almost surely capital F of NP is smaller than t. So t can be used for as an upper bound of capital F of NP. So with the suitable variables, it implies the upper bounds in B and C. So now to get the upper bound t, we need to choose some suitable variables t, omega, and sigma, which satisfies these two blue things, two blue conditions. So let's think about the upper bound in B, so which is about this part. So for this result, we need to show the following. There is a positive constant C such that the following holds with a high probability. When P is between n to the negative 2/3 and n to the negative 1/3, capital F of NP is smaller than some constant times n log n to the 1/3. So actually it is sufficient to prove when P is n to the negative 1/3, which is when P is the largest one. Because if P is the large, so if we have this upper bound, when P is the largest one, then if P is smaller, then the random set will be smaller, right? So the maximum size of the Sidon subset will be smaller. So for small p, we can have the same upper bound. So we only need to prove this when p is the largest one. So let's define variables. So p is the largest one, and t is this one, which is the upper bound of capital F of NP. And we will take omega as a big constant and sigma as a logarithm, one of the logarithm function. Then we need to show two conditions are satisfied. So first, let's think about the first condition. So with this choice, the left side is t cubed, which is, since t is c times n log n to the 1/3, t cubed will be some constant times n log n. And if we think the right side of the inequality, based on the choice of sigma, we can have this kind of computation, and we will have an upper bound of the right side as 4/3 omega cubed n log n. So by the choice of a large constant c, this left side is bigger than the right side. So we can show that this choice of t gives us an upper bound of capital F of P. So we need to do the second thing, second condition, with the same choices of variables, but let me skip this part. It's just computation. Okay, so and the upper bound in C is similar to the upper bound in B. So this is this case. So we need to show that there is a positive constant C such that the following holds with a high probability. So when P is greater than n to the 1/3, we want to show that capital F of NP is smaller than some constant times square root NP log n. So we will take some different variables. Then after that, we need to show that two conditions are satisfied. So we can, after computation, we can understand that this is true. So we can use this P as an upper bound of capital F of NP. So it remains to prove the key lemma to show the upper bound B and C, which is about the cardinality of the family of all Sidon sets of size T in the N set. The main idea of the proof is a Cayley graph. So actually, so if you see the result of this talk, the result is just about number theory. There is no graph, no hypergraph. But the proof of this result is based on graph theory and hypergraph theory, which is interesting. So for the upper bound, we will use Cayley graph. So first, let me define Cayley graph. So for an integer set A, we define Cayley graph of A as the edge-labeled graph. The vertex set of Cayley graph is the N set. And if U plus V mod N is in A, we add the edge U comma V to Cayley graph of A. And the edge U comma V has label U plus V mod N. So this Cayley graph has vertex set, edge set, and labels for edges. So let me give you an example for this. So we consider integers from 0 to 5, and we will think a subset A as 1, 3. So first, and we will think about the Cayley graph of A. So first, the vertex set of this Cayley graph will be the base set, which are integers from 0 to 5, like this. And then after that, let's think about the edges. So each element in A creates several edges for the Cayley graph. First, the element 1 is in A. So we have this kind of red edges because 1 plus 0 is 1, and 2 plus 5 is 7, which is 1 mod 6. And 3 plus 4 is 7, which is 1 mod 6. So we have this kind of edges, and we give the label 1 for each these edges. And on the other hand, the other element 3 in A generate different kinds of edges like this, because 1 plus 2 is 3, etc. So, and the Cayley graph of A will be the union of two things, which is like this. And we can observe the following thing. An integer set A contains a solution A1, A2, A3, A4 of x1 plus x2 is x3 plus x4 if and only if the Cayley graph of A contains a closed walk of length 4. So let me briefly explain this part. So let's assume that we have a solution like this. Then we will think the Cayley graph of A. So these AIs are in A. And if we will think Cayley graph of A. Then Cayley graph of A will have this kind of closed walk of length 4. So A1, A2, A3, A4. So let's think about the reason. So we can think arbitrarily vertex here. Let's say that is V. And this vertex will be A1 minus V, because by the definition of the Cayley graph, this number plus this number should be that. So this will be A1 minus V. And if we think this vertex, there will be A3 minus A1 plus V, because this plus this is A3. So in a similar way, this vertex will be A2 minus A3 plus A1 minus V, because this plus this should be A2. And this last vertex will be A4 minus A2 plus A3 minus A1 plus V. Since these are closed walk, this is a closed walk, the initial vertex is the same as the last vertex. So these two things are same, which means that after cancel V, we have A1 plus A2 is A3 plus A4. Right. So this is very nice thing. So when we have a set of integers to verify whether the set is a Sidon set or not, instead of thinking the non-trivial solution, we think the corresponding Cayley graph, and we check whether the corresponding Cayley graph contains a C4 or not, right? So, okay, so let me mention one more thing. So, and we are interested in non-trivial solution only. For that, we can add a weak additional condition. So as I mentioned before, so we can easily check whether a set is a Sidon set or not. So 1,3 is not a Sidon set. 1,3 is a Sidon set, right? Because there is no non-trivial solution. But we can check this as follows. So we can think the Cayley graph of A, and if we see this graph, there is no C4. So we can say this set A is not a Sidon set. So we will use this kind of observation later. Okay, so then we will think the following fact. So the situation is the following. So when we have a Sidon set, we will add several more elements, and we want to make a bigger Sidon set. So for that, we want to know what kind of element we can add or not. So let's think about this fact. So let A be a Sidon set, and let V is out of A. Let V be out of A. If W is a second neighbor of V in Cayley graph of A, like this, so V is connected to W is connected to V by a path of length 2, then we can say A union V comma W is not a Sidon set. So which means that if we add both V and W to A, the bigger set is not a Sidon set. So let's think about the proof. So to show this, it is enough to show that the Cayley graph of A union VW contains a C4. So if we first think the Cayley graph A, we have this kind of configuration. And then if we think the Cayley graph A union V comma W, we have trivial H between 0 and V and 0 and W. Because 0 plus V is V, and V is in this set, so we have this trivial, this H in the Cayley graph. Also, we have the H between 0 and W. So you can see C4 here. So, which means that A union VW is not a Sidon set.
Are you assuming that 0 is A, or?
So in this figure, it looks like that, but actually that it does not matter. So maybe 0 might be here, 0 might be here, but when we define the Cayley graph, so and the H doesn't depend on the vertex. So the H can start with any vertex. So even though 0 is here, between 0 and v there is edge. So yeah, so this figure is a little bit wrong because 0 might be out of A. So what we want to do is to prove the key lemma, which is to bound the cardinality of B of t, where B of t is the family of all Sidon sets of size t in the N set. So let's explain outline of the proof. So we want to count a Sidon set of size t. For this, to do that, we will divide B into 3 small subsets, B0, B1, B2. Maybe the size of that is t over 3. And let's say that is S. Then first, so we will think this kind of B0, B1, B2, and we will estimate the possible number of B0, B1, B2 separately, then, so which gives us an upper bound for the cardinality of B of t. So first, let B0 be an arbitrarily Sidon set of size S. B0 is used to generate the calligraph of B0. And we add another S set B1, A1 through AS to B0 to create a bigger set, B0 union B1. And then this creates new obstructions to make a bigger Sidon set, because the second neighbor of an element of B1 in the calligraph of B0 can't be chosen as the remaining t minus 2s elements. The reason is the following. So is from here. So let's say this is B0, and we add this kind of element. So let's say V is in B1, then we will think B0 union B1. Then when we try to make a bigger Sidon set, we can't add this kind of element W, because if we add this also in the set, this fact tells that the bigger set is not a Sidon set. Okay, so the thing is the following: the second neighbor of an element of B1 in calligraph of B0 can't be chosen as the remaining t minus 2s elements. So let CS plus 1 be the set of candidates for the remaining elements AS plus 1 through AT minus S. Then we showed the size of CS plus 1 is less than or equal to 1 over S sigma times N. So I will skip the proof of this, but the main idea, ingredient for this upper bound is from these constructions, these obstructions. So, and this bound is pretty good, because when we think these variables, S is greater than n to the 1/3, and sigma is a kind of constant or logarithm function. So this part, 1 over S sigma, this whole thing is smaller than n to the 2/3. So this is much smaller than n, so which is a good thing. So with this proposition, let's try to bound the cardinality of B of t. So the B of t, the cardinality of B of t is smaller than the choice of S at B0 times the choice of S at B1 times the choice of the remaining t minus 2s set. And first two things can be bounded by natural upper bound n choose S. And the last one can be bounded by Cs plus 1. The candidate says Cs plus 1 choose t minus 2s because the remaining t minus 2s set element should be chosen from this candidate set. And if we apply this proposition, then we can have our key lemma. Okay, so actually the upper bound was the most non-trivial part in this talk, so let's think about lower bound briefly. So first, let me mention about the lower bound in B, which is this part from below. So for this result, we need to show the following. There is a positive absolute constant C such that the following holds with a high probability. When P is between n to the negative 2/3 and n to the negative 1/3, capital F of NP is greater than some constant times n log n to the 1/3. Oh, okay. But for a simpler explanation, let me explain a little bit weaker lower bound n to the 1/3. For this, we will define a hypergraph S as follows. The vertex set of S is the n set. For every non-trivial solution of x1 plus x2 is y1 plus y2, we add the hyperedge a1, a2, a3, a4 to S. So, for example, so let me draw the hypergraph. So first, vertex set is from 1 to, the integers from 1 to n. And if we have a non-trivial solution, then we create a hyperedge like this. Then we may have hyperedge like this. Okay. And let S of NP denote the subhypergraph of S induced on NP. So now we are interested in the random set. So let's think about induced subgraph F of NP. Then we can understand the following. The set U is an independent set in S of NP if and only if U is a Sidon subset of NP. This, because if there is an independent set here, if there is an independent set U here, which does not contain any hyperedge here, means that this U does not contain any non-trivial solution. So U is a Sidon subset of NP. So the problem about the Sidon set can be translated to a problem about independent set or independence number of the hypergraph S of NP. And Turan's theorem for a K-uniform hypergraph implies the following. Let H be a k-uniform hypergraph on n vertices, then the independence number of the hypergraph is greater than some constant times the number of vertices over the average vertex to the 1 over k minus 1. And we can estimate the number of vertices and the average degree for this hypergraph S of NP. Then we can have this kind of numbers, and we can get this lower bound for the independence number. So for expectation is not so hard. And for the concentration, you need to apply Chebyshev's inequality, where for better concentration, you can apply Gindu's polynomial concentration. Then, therefore, this lower bound of the independence number can be used as the lower bound of capital F of NP. So we can have this kind of lower bound. And next, the last thing is the lower bound in C, which is this part from below. So for that, we need to show the following. There is a positive absolute constant C such that the following holds with a high probability. When P is greater than n to the negative 1/3, capital F of NP is greater than some constant times square root to NP. Idea of the proof is the following. So we consider a partition of n as intervals of length 2 over p. Then we will have np over 2 intervals. And then we will apply the maximum size of a Sidon subset of integers of size np over 2 by the Charles result in 1940s, which is about integer set. Then let me show you the figures about this. So first we have integers from 1 to n, and we consider a partition of n as intervals of length 2 over p. So this size is 2 over p. Then we divide each interval into 2 sub-intervals of length 1 over p. So the size of this first half of each interval is 1 over p. Then we correspond each interval to an integer from 1 to np over 2. This is errata, this is np over 2. Then, by the Charles result in 1940s, we know that this np over 2 integers contains a Sidon subset of size square root to np over 2. So let's say that is this vertices in the red region. And we consider the corresponding intervals. And after that, we expose a random set independently with the probability p. Then, now we want to choose a Sidon set in the random set here. So if the first half of each interval contains a random element, we choose the element. So for example, in the first interval, first interval does not contain any random element in the first half, then we have nothing to choose for the Sidon set. And if we see the second interval, there is one random element in the first half, so we can choose that element for our desired Sidon set. And if the first half contains 2 elements or more than that, then we arbitrarily choose one of them, and we take that as an element of our desired Sidon subset. Then, so we need to show, first we need to show that this kind of set of this kind of elements are Sidon set. So let me explain that. So we have two elements, A1, A2, and A1 is in I1, II1, and II2. And let's say this element is A3, which is in II3. This one is in II4. So this index is about the index of the interval. Then we can think the corresponding index, I1, so I3, I4, I1, I2. Then since these below elements are in the Sidon set, what we know that is I1 plus I2 is not the same as I3 plus I4, because we think Sidon set below in here. So this means that so and what we know is I1 plus I2 should be in the interval I1 plus I2, because we choose each element from the first half. Then, so for example, if this is in the first interval and this is in the third interval, then the sum should be maybe in the fourth interval or fifth interval. But since we choose those elements from the first half of each interval, there is no carry. So this element should be in the interval should be in the I1 plus I2 interval. So in the same reason, A3 plus A4 is in II3 plus I4. But based on this region, two intervals are distinct. So this element should be different from the other element. So this is a kind of nice tool, how to use some information about intervals for a random set. So, and the last thing we need to do is to count the number of those elements. So first, we know that the number of intervals in the red region is square root np over 2. So what we need to think about is the probability that one interval contains a random element in the first half. Actually, each interval contains 1 over p elements in the first half, and we will choose each element with the probability p. So if we think the number of random elements in the first half of each interval, that will be something like the Poisson distribution. So we know that with a positive constant probability, the half of each interval contains a random element. Let's say the constant is c, then we know that we can pick c times square root np elements. So this is the end of the proof. So I passed the time. So let me can I take one more minute? Yeah. So let me briefly mention about open problem. So first open problem is from our main result. So if it's in the result C, the lower and upper bound of capital F of np is square root np and square root np log n. So there is some gap here. So if someone can reduce this upper bound to square root np, we can determine the behavior of capital F of np up to a constant factor for every p. And second thing is to study the behavior of an infinite Sidon set in a random subset of the n set. Not n set, of the set of natural numbers. So actually, I'm working with this with other two authors, and we got some answer of this recently. And the last thing is to study the maximum size of a Sidon set in a random subset of a finite Abelian group. So first, we show that the same result holds in the cyclic group Zn. So next problem will be about a finite Abelian group. So thank you very much.